Hello everyone, this is the Atom Test Review. Question 1. And actually the first 5 questions were about scientists in history that helped us develop the atomic theory we've been studying. I didn't include everyone, but I included some of the more famous guys. So John Dalton, around 1800, used experimental evidence based on the work of Proust and Avogadro to develop the idea of matter being made of atoms, kind of like Democritus did a couple thousand years earlier, but this time John Dalton, he had proof of what was going on based on experimental evidence. So he developed this theory, and he was right except for the idea of isotopes, and of course he didn't know about subatomic particles. Number 2, I showed a video in class of J.J. Thomson shooting, or actually as a science teacher, shooting a stream of electrons. J.J. Thomson did this, put a magnet next to the electrons, and the electrons bent. So J.J. Thomson is the electron guy, gets most credit for discovering electrons. Bear in mind that all these guys did work, but a lot of people did work, and they're the people that got the most credit for it. Ernest Rutherford was around 1900s, in the early 1900s, shot gold foil, shot alpha particles through gold foil, found that the alpha particles, and by the way, an alpha particle is a helium nucleus. He shot the alpha particles through the gold foil. Most of them just went straight through without being disturbed, which showed that the atom was empty space. I used the analogy in class that if the atom was the size of Busch Stadium, the nucleus would be about the size of a tennis ball in the center, and the rest of the atom would just be empty space, except for the fast-moving electrons. And it's kind of like if we talked about a ceiling fan. You don't really know where the blades are in a ceiling fan at any given point in time. But if you put your hand up there where the blades are, you'll find a blade. And that's the way electrons are. So if we're going to describe electrons, we can't describe them as particles. I can't say, well, the particle's sitting here or the particle's sitting over on the other side of the atom. Because anytime you could see them, you would change where they are because they're so lightweight. And that was called the Heisenberg uncertainty principle. And taking a pause between 4 and 5 for just a second, since we can't treat electrons as particles, de Broglie had found out that, de Broglie, D-E-B-R-O-G-L-I-E, had found that electrons or particles, pieces of matter, can have a wavelength. And in class we calculated the wavelength of a duck, which turned out to be negligible, but we also calculated the wavelength of an electron, which turned out to be significant relative to the size of the atom. So Schrödinger used calculus to calculate shapes, regions in space where you'd find electrons, and that's where the pictures of the orbitals that we've been talking about come from. All right, so now going back to where those electrons are in terms of their energies, one of the first models of the atom was the ring model, or the solar system model, that was developed by Niels Bohr. In class, to illustrate that, we used the spectrum light tubes and the diffraction grating glasses and looked at the lines of light. And the lines of light show us that the electrons only can exist at certain places in the atom. They can't just be anywhere. All right, number 6, neutrons in an atom of 24, or sodium 24. So that means that you have 24 protons and neutrons together. If you subtract the number of protons in sodium, that will give you the number of neutrons. So the answer was D. Number 7, the number of electrons you'd find in a -2 ion of sulfur. If the charge is negative, that means a gain of electrons. So the correct answer would be 18, because sulfur normally has 16 electrons, and if you gain 2, to get a -2 charge, you'll have 18. Okay, paramagnetic means it has the most unpaired electrons. If you look at nickel, it'll be a 4s2, 3d8. Cobalt would be a 4s2, 3d7. Copper would be a 4s2, 3d9. Chromium would be a 4s2, 3d4. And vanadium would be a 4s2, 3d3. All right, so paramagnetic, having the most unpaired electrons, let's do it this way, would mean which has the most unpaired electrons in a d sublevel. Well, the d sublevel has 5 orbitals, so you would end up with in the 5 orbitals 2 electrons, 2 electrons, 2 electrons, 1 and 1. For cobalt, it would be, this is in the d sublevel now again, 2, 2, 1, 1, 1. Does that make 7? Yes. In the copper, you'd end up with 2, 2, 2, 2, 1. And really what happens in copper, just for the record, is 2, 2, 2, 2, 2, because one of the electrons from the 4s here gets promoted and comes over here and becomes a D10. That we talked about some exceptions to the filling order, and this is one of the exceptions to the filling order, or the Aufbau principle. Chromium then would be 2, no, it would be just 1, 1, 1, 1, because there are only 4 electrons, so they would all go in by themselves. They wouldn't have enough electrons to start pairing up. Remember that the electrons fill the d orbitals one at a time before they begin to pair. And vanadium's d sublevel would just be, there are 3 electrons, 1, 1, 1. Of course, if I was really doing this correctly and not trying to go kind of quickly on a computer, you would need to superscript these guys to make them look in correct notation. All right, number 9 dealt with when an atom moves to a lower energy level. I wanted you to learn 2 things from this question, or this question is kind of reminding you of 2 things. First of all, when the electron goes to a lower energy from a higher energy level, energy is released. So released is the correct answer. It's either going to be A or C. Max Planck is another one of the famous guys who developed the idea, along with Einstein and the photoelectric effect. To show you the photoelectric effect, one day we threw paper wads at erasers and learned that the only way you can knock more erasers off, or actually I guess we did it with markers. So we threw paper wads at markers. The only way you can knock more markers off is to throw more paper wads. The photoelectric effect, that light travels in little packets, and it's quantized. So I wanted you to remember also that light, when it's released, it releases energy in definite quantities of light, because light travels in little packets of energy. So the correct answer would have been C. All right, number 10, the element in the 3rd series that has 5 valence electrons. Instead of writing all these configurations, I'm going to write the configuration for the correct answer, and you can try the ones for the incorrect ones if you'd like. But phosphorus is 1s2, and I'm not going to superscript for the sake of time on the internet here. These videos can get long. 1s2, 2s2, 2p6, 3s2, 3p3. Okay, so the 5 valence electrons show up in the S and the P sublevel of phosphorus. The S and the P. All right, number 11. I think I'm going to stop there, and I'll post this video in 4 parts in order to avoid having them be quite so long. It takes so long to download and stream in and such. All right, so magnesium will have 2 valence electrons, silicon will have 4 valence electrons, chlorine will have 7 valence electrons, and argon will have 8 valence electrons. Remember, valence means outer shell, or highest energy level.